Thank you so much to our organizers who joined the webinar to present the latest trends in memory disaggregation. So at that point, I'm just going to turn it over to our first speaker.
Okay, so first of all, good morning and good afternoon and good evening, everybody. Thanks very much for taking the time for joining us in this exciting discussion today. I'm Christian Pinto from IBM Research Europe in Ireland, and I have organized this webinar together with Peter Hofstee from IBM as well, and also TU Delft. And then, first of all, thanks very much to the OpenCAPI consortium for giving us a roof for this webinar. So Myron and Alan have been supporting us from the OpenCAPI consortium, and also thanks very much to Joan. She's been handling our communication, setting up the website and everything. So thanks very much, everybody, for making this happen. So let's start, right? So what is first of all the rules of the house? So this event is being recorded. So if you're not fine with that, we are sorry, but we are recording, so for later you can watch it on YouTube. And please keep your mic in mute during the webinar. We will have a single Q&A session at the end of this event. And in the meantime, during the presentation, you can post your questions into the Q&A chat, so that this way we will be reading them during the Q&A, and the speakers will take the time to respond. And then the last thing is that we just hope you enjoy the amazing content you are going to listen to. So this webinar is about memory disaggregation. I won't spend too much time on it because our speakers will fill you in with enough information. So basically, memory disaggregation is that you have your applications accessing memory, but this memory is not local to the system where they are running. This memory is actually being borrowed or used from a remote machine. This remote machine can either have a CPU or not. This depends on the configuration of memory disaggregation that you're using, basically. And this is quite a, let's say, new concept in the sense that you don't find this in any CPU yet, but there is a way for you to work with memory disaggregation today, and it is by using Power 9 machines. And thanks to OpenCAPI and the TMSIS Flow prototype, which is a project of ours at IBM Research, we are basically able to implement a memory borrowing system across Power 9 machines. And all of this is possible because of the coherent attachment that OpenCAPI enables. In this webinar, we're going to talk about future trends in memory disaggregation. So meaning what is that is going to happen beyond this prototype based on Power 9 and TMSIS Flow. So what are the news there? And also some exciting research that is happening right now, and that is leveraging this configuration, so with the TMSIS Flow prototype and Power 9. Our first speaker is Alan Cantel. He's the CEO of Nalansway, that is a consulting firm on heterogeneous and high-performance computing systems. But he is also the OpenCAPI Consortium Technical Director. Previously, he was the founder of Nalatet, that is known as one of the pioneers of FPGA accelerated computing. So Alan will, let's say, drive us through what is OMI and how is OMI helping in enabling a flexible and composable computing system. So we're going to talk about memory interfaces with Alan. The next speaker, it will be Stephen Roberts. He's a senior technical staff member at IBM, and he has served as architect for 7 high-performance machines that landed in the top 500 supercomputers list. And he also served as chief engineer for Summit and Sierra. And Stephen will present us commercial adoption of memory disaggregation. So basically, the upcoming Power 10 CPUs will be the first CPUs on the market enabling this type of technology. that in the case of Power 10 is called Memory Inception. So Stephen will talk about Memory Inception and some of the use cases behind it. Then we will switch to Felix Heberhart. Felix is a researcher at the Hasso-Plattner Institute in Germany, and his research interests are around analysis and optimization of workloads in scale-up systems. And Felix will discuss about some, let's say, new challenges at the operating system and application level for that are, let's say, created by memory disaggregation. And we will talk also about a possible use case. And finally, we'll have Akos Adnagi. He's a researcher at the TU Delft in the Netherlands. He's interested in digital design and accelerated computing in general. And in his talk, he will drive us through how to exploit memory disaggregation for big data analytics, and he will also describe some changes and enhancements that they are doing to the T-Mesis flow. They are contributing to the T-Mesis flow prototype for enabling their work. So without any further delay, let's start with our first speaker, Alan. The stage is yours.
Thank you, Christian. Let me just check that I can share my screen here. Can you see that okay?
I want to go into screen show, but we can see it.
You can see this. You can see it. Okay, good.
Yeah, you can go in full screen mode, please, so that we see the full slide. Thanks.
Yeah. Okay, can you see the full slide now?
Yeah, now it's great.
Okay, let me start then. Okay, good morning, everybody. My name's Alan Cantle, and welcome to the trends in memory disaggregation. I'm going to be specifically talking about the Open Memory Interface, shortened to OMI, and hopefully showing you that why this is a missing piece in a disaggregated, modular, flexible, and composable computing world. And so I'm going to be focusing on this. When we look at disaggregation as a whole, we absolutely need to be able to compose our systems very well, and so I'm focusing on the OMI piece and leaving the others to talk about the actual sharing nature that's going on. So I'll try and set the scene for these guys as well as give you a background into the OMI interface itself. So first of all, what is disaggregation? Sorry, I'm not sure if I can move it. Let me try and move this. Okay. First of all, what is disaggregation? So effectively, it's an attempt to free up stranded resources for differing workloads. On the left here, I've shown a classic server of a typical converged infrastructure, and I've made cartoon blocks of the various resources that you can see here inside a server. Now, when you run a particular workload, you will typically use more or less of each of these resources. And the challenge is often these resources will get stranded and unreachable by other nodes. And so the desire is to disaggregate this and make it more reachable by everybody. And so one technique for this is rack scale disaggregation has been tried in the past, where literally you split each of the resources into a separate chassis level box, and then you re-aggregate them back together with your favorite fabric, being either Ethernet or PCI, and potentially future support for CXL. The resources are allocated and managed with Composer software, allocating the appropriate resources to each virtual machine-driven workload. And hopefully you don't get any stranded resources with this approach. Now, unfortunately, this approach actually comes with some significant disadvantages as well. So whilst you get the resources back, you have more challenges. So the downsides of rack scale disaggregation are, you actually increase the power through more data movement. So these resources are now further apart. So when you connect them back together with the software, you're burning more power. And you're putting more stress on the network to actually enable the software composability. So whilst logically it makes a lot of sense, practically it can be challenging. And it gets worse because from a memory perspective, disaggregating local DDR memory into memory pools has proven to be more challenging. Fundamentally because we are talking about this being latency critical, and also reliability, availability, and serviceability issues with this approach. So hence why this is an interesting topic for us to be talking about today, and this area is the focus of this webinar. I'm going to be talking about all of this in terms of the disaggregation and composability of everything. And my colleagues will talk in more detail on this area. And to give you a little bit of a teaser as to where this is going, is really we are still proposing that potentially memory can be should still be tightly coupled to its local CPU, but we need better mechanisms for sharing that local memory whenever is needed. So on the left we can see we've got the Phymesis flow, which is essentially sharing your local memory over your favorite fabric, as we'll hear from the other presenters, and also natively in Power 10, as Christian mentioned, we're going to see Memory Inception used for sharing memory over OpenCAPI. So hopefully that gives you that sets the scene for everybody. So continuing with my broader scope and focus on the memory itself. Why do workloads differ in resource needs? So differing compute ratio is basically because of differing compute ratios. We've got operations to bytes per second to bytes of capacity as our classic ratio comparison. And if we separate these into three extremes, we can see we've got the processor centric, where the compute ratio is very flops biased, and with decent memory bandwidth and not much memory capacity. So a good example of that, just one example, is like a GPU with its HBM attached memory. The more traditional approach is the balanced classical 1-to-1-to-1 configuration that your standard CPUs and servers have tried to maintain, albeit very challenging over the years. And hence why we've had these increasing complexity of cache hierarchies. And finally, you've got the data-centric, which has become popular over the last 10 to 15 years, where you're very data-heavy, memory-heavy, with good bandwidth, but really fairly little processing requirements. So these are the sorts of workloads that put challenges on a standard server configuration. But it doesn't stop there, because in reality, when you come to a specific application, you will have workload algorithms that exhibit these compute ratios, these differing compute ratios. And they will be running in parallel and communicating with each other with different bandwidth demands between these algorithms. And so that presents an even wider challenge in terms of composing the ideal infrastructure. Effectively, you can say, look, the compute ratio, no matter what level you look at it, hierarchically, either at the data center level, the rack level, the server level, the module level, or the silicon level, we're seeing these ratios play out at various different levels. And so the complexity of this is, in terms of getting a perfect balance for your application, is challenging. So, but if you could compose a computer to applications A's exact needs, you now have a domain-specific architecture, as defined by Hennessy and Patterson, the two gods of computing architecture. And that's the trend that they've been saying our industry needs to go in to get more and more out of compute performance. But building applications A's exact architecture requires modularity, flexibility, and composability everywhere. Every aspect needs to be there for us to be able to succeed in building these domain-specific architectures. So, question is, can we disaggregate without the downsides of the rat scale example that I gave you? So really, we need to be able to physically have this modular, flexible, and composable architecture. And so taking my simplistic application A example, could we actually build a Lego block type construction of those compute ratios in a very dense and modular fashion and connect everything together like this in an idealistic situation? If we could, then domain-specific implementations could be quickly configured and tested as well, if we could actually build such an architecture. And if we could get the dense modularity and we have this distributed computing with all the communications going on, computing everywhere, then we really will truly minimize the data movement power, because we'll be moving data less often, and the tight coupling will keep things together. So switching gears back to the memory then for a moment, DDR is a parallel interface in a serial world, and it's absolutely unsuitable for physically composable systems. So if we take a look on the left, we can see that the rest of the resources have gone serial for a long period of time now. And actually, they're coming together into industry standard interconnect. We can see the OCP NIC-free, the storage drives, NVMe storage drives in E3.S and E1.S formats, and you have miniaturized cabled I/O as well, all in this same format that gives us potential composability. And now we can say that we've got OMI, which is in the same serial format with the same interconnect technology. So suddenly we filled this missing piece. And this is what I mean by the missing piece in a composable world, where DDR DIMMs just do not live. But OMI offers far more than just composability. That is a very attractive aspect all by itself to make it worth a closer analysis. But let's take a closer look at the OMI differential DIMM. You can see a picture of the real card in the top right-hand corner, but in the bottom left, you can see that there's a couple of different form factors growing in height to suit different capacities. And also for reference, I put it to scale against a standard DDR4 DIMM. So one of the big advantages, or the big necessity, should I say, of going serial with memory is latency. It is super critical for latency, and this is arguably why the memory channel has been the last one to be serialized. OMI has achieved a fundamentally amazing latency adder over the standard DRAM channel of less than 10 nanoseconds versus a standard DDR4 RDIMM. And this is absolutely fundamental. Otherwise, this doesn't work. And arguably as well, another thing is transceiver speeds have been playing a great deal of catch up recently that really does make them more viable as well for serial attached memory. This module has actually been in production since mid-2019 and is available from Samsung, Smart Modular, and Micron. And so, it's a relatively mature technology. The memory channel itself is completely technology agnostic. So that will allow easy migration, for example, between DDR4 and DDR5. So if you're a processor company and you're trying to work out whether you want to design your next very expensive tens of $1 million processors to connect to DDR4 or DDR5, you're trying to second guess the adoption of DDR5. you don't need to do that anymore. You could implement the OMI interface, and as in when the market dictates that DDR5 becomes more cost effective than DDR4, etc., you can swap your DIMMs on a business or opportunity basis. So that the OMI gives you that wonderful option there. Also, a really big advantage is we've got up to 8 times more memory bandwidth per processor. So the differential DIMM itself is twice the bandwidth today of a standard DDR4 DIMM. And as you can see from the picture below, we can actually fit 4 times as many channels into a standard processor package in comparison to a DDR4 channels. Finally, we've got some very good ecosystem enablement with some Fpga host and buffer bring-up platforms shown on the bottom right. The IP here, so if you're developing your own processor, you can experiment with your own IP on top of the OMI interface. And likewise, if you're developing your own buffer memory, again, we've got this bring-up platform for your own custom OMI DIMMs. Basically, all of the IP here, everything you're seeing is fully open sourced for the host controller and the OMI memory buffer. The RTL is in GitHub, and it also includes functional and memory traffic generators for testing purposes, so you can actually test out your entire memory channel. So again, this is all very encouraging information. But really, pulling all this together, the OMI advantage, simply put, is memory bandwidth and capacity at low cost. So I've put together a couple of these die diagrams to try and emphasize this for everybody. So in the middle is and this is all to scale, by the way. So the IBM Power 10 die is shown with 16 OMI channels, 8 on the left and 8 on the right. And if we take on the left-hand side, we've also got the AMD EPYC Rome IO die with 4 DDR4 memory channels on one edge as a beachfront comparison between the two. So from a beachfront perspective, we can see that we're roughly the same 8 OMI channels roughly consumes the same beachfront as 4 DDR4 memory channels on the EPYC die. But it's important to note that the DDR4 channels have to be stacked too deep to match the single deep 8 OMI channels. So from an area perspective, you're winning out even more. And I believe IBM have said you get a 6 times area improvement by going to OMI on your processor compared to DDR. And so that's very valuable to the processor companies wanting to get more compute or indeed more memory channels out of their processor for more bandwidth. Not only that, capacity for DDR has been shrinking. For those of you observing the last few years, you've seen us go from 4 DIMMs per channel to 2 and now to 1, especially if you want to get the bandwidth out of the DDR. So memory has been shrinking on the DDR side, whereas the OMI is giving you more channels, so more DIMMs, and the speed remains the same, and which improves. And you can see the comparison here. We've got 100 gigabytes per second versus 400 gigabytes per second on OMI, so a 4 times improvement in this example. If we flip it onto the other side and we take a closer look at HBM, which is really the high bandwidth memory, giving you sheer bandwidth that is actually needed for some of these processors, I've shown the NVIDIA Ampere die as a comparison here. And if we compare 1 HBM channel with 8 OMI channels, once again, we are consuming very similar beachfronts of the die, of the processor dies for that memory. Interestingly, if you look into the HBM architecture, it's actually split into 8 independent channels of separate read and separate write ports. So architecturally and logically, it's very similar to 8 OMI channels, which is quite interesting from my perspective. But if we compare the bandwidth, actually the OMI is giving more bandwidth than the HBM for the relative beachfront area, 400 gigabytes per second versus 311 on the NVIDIA Ampere. Now, and the HBM actually comes with a bunch of baggage as well. It's on package, so therefore you are constrained with the amount of memory you can add. It's relatively low resources. It increases your thermal challenge and your power challenge on the same substrate. And
Alan, you have 2 minutes left. Sorry.
Okay. Yeah. Okay. Thanks. And as well as that, you on the HBM, and as well as that, you are you get the capacity the vendor gives you. You cannot configure your own capacity. So that's the benefit of OMI, which really is a no-brainer in my sense. I've never seen something so compelling in my entire career, and it seems like a really, it makes sense for the industry to move in this direction. If we go back to the composability side, can we build this Lego block approach? So leverage from the OCP's OAM module is something I've been looking into, and which is quite a, relatively speaking, small module with very powerful processors. But I've changed the interconnect. I've nicknamed this OAM HPC, but we've changed the interconnect to these IOs. That all of the media and IOs are actually using this EDSFF interconnect. And so if we look, we can see that with an FPGA, we could have cabled IO, OMI differential DIMMs connected, the E1.S module connected, E3.S, or the OCP NIC 3.0, all connected into the same module, giving you true composability. And just for good measure, I've shown a mix of all of the technologies in one module. And obviously an FPGA with its configurable firmware can give us complete access to these different configurations. And so we've got this true Lego block composability in a very dense module here, which is quite attractive. If we look at it from a Power 10's perspective, building the same module with a Power 10, it's obviously got its specific OMI interfaces, so we can configure that with 16 OMI DDIMMs, and its cabled IO for OpenCAPI, SMP, and/or PCI. So, and again, you can have any other modules as well with different processors, and you can mix and match these processors for your particular application. Finally, putting all this together, and I've specifically put it together in a memory pooling example, where every one of the modules is filled with OMI differential DIMMs, we can see the potential to actually scale this up. And again, the modules here, there's a total of 256 modules with 8 terabytes of memory. This is architected that it would actually fit into an OCP OAI chassis. And it could be a memory pooling server in the OCP environment, where the cabled IO would be could carry the disaggregation through Mimesis Flow or OpenCAPI, etc. So thank you for that. Thank you for the talk. That's my presentation. If you would like to find out more about OMI or the OEM HPC module, please contact me on that email address. Thanks very much.
Thanks a lot, Alan. It was a very, very interesting talk. We'll have some questions at the end. I'm sure there will be. At least I have. And okay, so now with no further delay, we'll switch to our next speaker, Stephen Roberts. Stephen, the stage is yours.
All right. Can you hear me okay, Christian?
Yes, I can hear you okay. I can't see your screen though. Okay, now I see. Now we see your screen. Yeah.
Great. Good. All right. Well, thank you for the kind introduction. I appreciate that. And Alan, thanks for setting the stage for what I'm going to talk about here too. I'm excited to share some insights on our new Power 10 feature, Memory Inception. This is built upon OpenCAPI, and it's meant to provide a streamlined CPU to CPU memory interface. This talk is a byproduct of the work that Christian Pinto and David Christensen and I are doing on the Mimesis Flow system in preparation for Power 10 systems. And my aim is really to inspire the Mises Flow community and the memory disaggregation community to start to think about how their endeavors can continue on Power 10 systems. So we'll start with an agenda which builds from the current technologies onto tomorrow's capabilities. We'll get into the memory inception flows, talk about point-to-point data models in the most simplistic of terms, right? Borrowing, producer-consumer type of models. And I have to put truth sharing on here, but we're not going to talk about truth sharing. Truth sharing is the domain of the SMP system, and where you want to share everything from memory to I/O to down to the cache level. And the memory inception technology is not that. We are able to, MI gives you the ability to be coherent within a system or node, but not beyond a single system. So we'll go over the nuances of that and then expand upon how you can take advantage of what MI gives you. And that's really that it provides a different functionality orthogonal to what SMP systems do. It gives you a scale out well beyond what you could do with SMP systems, up to the scale outs up to about 1,000 endpoints. And to be able to maintain the state and to share the cache state or keep track of everybody's caches at that scale, it would just be unachievable. So we're not going to talk about truth sharing, but we'll talk about how to get as close to it as you can given the MI infrastructure. And we'll go beyond the point-to-point interfaces at the end and talk about how the protocols like, well, I want you to think about at least how protocols like OpenSHMEM and OpenFAM could be realized on top of the MI technology. And hopefully I'm able to explain the MI technology enough that you can start to draw those conclusions and get ready for what can be. So we'll start with the OpenCAPI protocol stack. I mean, hopefully if you're within this community, you've recognized this. I've taken it, lifted it right from the OpenCAPI LPC memory agent reference design. I do have a reference to that design later in the presentation, but you see here a host CPU where the TLDL and Phi are described by the OpenCAPI protocol stack. And the system on the right is a FPU. Typically, the area in the red rectangle is implemented as an FPGA or even an ASIC accelerator. And these are the accelerator model, as we know it, where these two regions are able to coherently share data back and forth. When we progress beyond that model with the Mises flow, you start to you integrate basically this connection, these AFU connections between two hosts. So the FPGAs have hard IP, SerDes type of interfaces that can connect each other together. And if you implement the AFU on the core side as a memory agent and on the blender side as the DMA agent, you're able to connect a link where the host on the left, to the P9 host on the left, is able to do load store accesses to host memory on the right, with the Mises flow system. And then you can even extend this system, beyond this setup to the more complicated setup where you run the share the memory in the opposite direction with the addition of two more FPGAs to create a symmetric system in that case. So this is the system we've used for prototyping. And now I need to ask you to consider what happens if you move the memory agent over to the core of the borrower and the DMA agent over to the P9 host memory complex of the lender. And that's when we really start to think about what's possible and that's what we've implemented in P10. So in this diagram, you can see that we don't have the FPGAs involved in the system anymore, but we have the MI now built on top of the previous OpenCAPI work, acting as a home agent on the borrower and a accelerator agent on the lender, right? And as a result, we're able to do load store accesses. We were able to do those accesses local, or act like as if those accesses are local to the borrower domain. So in this case, on the left-hand side, the borrower is able to have consistency, a consistent cache hierarchy, a consistent memory view, within that domain. And then on the right, you're able to service the loads in the stores, and whether or not you allow processes to access the same OMI memory, dictate whether you're borrowing or sharing. But really the semantics on the far system are IO type of semantics, and it's and you don't have coherency with any processes resident on that node. So effectively here, the MI home agent is acting similar to the OMI memory agent, at least in principal function, except that the memory map allocated, the memory regions set up, the memory bar setup in the MI memory home agent are of course different than the OMI home memory agent. But for a practical example, they're serving a very similar function here from a programmatic point of view. So if we dig a little bit deeper about how addressing is done, we have it's standard effective address to real address conversion happening on the cache core of the borrower side. And this is done with traditional page table mechanisms. And the RA bar on the memory home agent is set up to receive those commands, translate that address to a physical address, a larger physical address, to enable it to go across the link to the MI agent, which does the reverse order translation and gets the transaction put on the power bus to be consumed by the OMI home agent. If you think about this on the borrower, this could a cut and paste type of transaction, or copy paste. I'm sorry, copy paste. It's a ISA defined pairing of commands. I did present that reference as well in the bottom of the book, but it basically allows the borrower to take to target a physical memory address on the borrowed system, copy that into a hidden state buffer, and then paste that out to the memory agent with relaxed ordering rules to allow a physical copy into the memory agent and transaction to be realized between the buses, a memory write, whereas the lender agent, the accelerator agent here, translates that into a DMA write into the OMI home agent. So that's how this is accomplished, the mechanism, but it can be extended even one further because we have a network mode, which doesn't have the load store semantics, but it accomplishes communication with a one-way store write. You can think about the vision here as, we're going to use the 2 petabyte global address space that's available in the architecture to map these shared regions. And those regions then dictate the route tables that have to happen along each step of this chain, where there's routing information that needs to be available in the accelerator agents, and of course within the local memory maps of the nodes that where the transaction passes through. So the bars need to get set up, and some of these translation tables need to be set up based off of that shared global address space. And with 2 petabytes to work with, we can produce those kind of constructs. So in here, the transactions are moved from one node to the next. Translation happens across the way, and the virtual channel support's incorporated into the hardware to make this happen, and to make it happen without device driver intervention. So in here, if we look at the deeper view, the translation is much the same, except that on the intermediate node on the right-hand side of the screen, you don't get RA hit at the OMI home agent. Instead, you get that hit at the another MI memory home agent, which then forwards basically the transaction to the endpoint, which in this example has the OMI host memory agent acknowledges at the final hop. So if you want the two-way communication, of course, you would need to establish that memory region sharing in the reverse order so that you could write back. And I'll give you an example of that later on in the talk. So let's think about this. That was kind of the hardware type of explanation of what's going on with the commands on the buses. But let's talk about this in terms of how it could be used from a programming standpoint and the data models, right? First of all, this is the most simplistic data model, which is point-to-point memory borrowing. And the reason that this is simplistic is because it's an exclusive model where you have hypervisors establish the memory maps on both sides, and you can configure the hardware and the set up the bars for both of these systems. And also, once this gets set up, you can think about it as a topology kind of represented here on the bottom right, where you have in this case, a 6 terabyte node, which is sharing data with the smaller node B, C, D, and E, which only have 16 gigabytes. And so if a VM, for instance, on node B needs to grow beyond the 16 gigabytes, or it can borrow from node A. And in this borrowing type of model, the processes on node A would be restricted from accessing that region. So that makes it a fairly simple setup in terms of, I should hide this, a fairly simple setup in terms of usage, and the consistency model is exclusive to the node B in this example, right? But when you realize this, an application can, the OS actually can make the memory available as a NUMA memory, and then an application can malloc, mmap, etc. And of course, as a NUMA memory, you're able to put a distance. And so as the operating systems become more sophisticated and you see more memory tiering type of functionality within, you have the application has the ability to blindly malloc into the regions and have the OS be at the victim of the OS as to where this is placed, and work as it would memory across sockets, for instance. Or an application that's more savvy can use mmap and take a look at the NUMA tables to effectively use that borrowed region and reduce any latency effects that might be a result of the span between node A and node B. So really, that's the easiest model, but it's also the model where the application can use memory outside of the node and not need to be modified to do so. We get into more sophisticated models when we start to talk about how data can be shared. And now I kind of broke this up into two cases. One of them, the first one is like the idea of an accelerator, where you have the node B, the processes within node B needing to act on a larger problem that's owned by node A. And in this case, node A makes the region available to node B to borrow, but the model here is going to be more of an IO model for node B because it's working on the borrowed region. It wants to cache the borrowed regions, the reads, but it's constructing that, taking that information and doing localized constructions in its own physical memory to create the return result. And so, after it's done with the borrowed region and done with the operation, it needs to post back its own physical memory, and it can do so via the borrowed region. And you can use the same cut and paste mechanism I described earlier to do that. To make that all work, you have to set up the mmap with specialized memory flags to basically tell the system, hey, I'm going to treat this as IO memory. I want to cache the reads, but I want to be able to use the cut and paste buffer to relax the ordering that I push the stuff back to region B. And then, of course, you have to have a mechanism to tell, for B to tell A, hey, I'm done, right? And that could be accomplished in different ways. The other use case here is the frame buffer type of use case, where region B in this case may be larger than anything that you can process with the physical memory available with node B. You still need the CPU offload, but you don't necessarily want to transfer the entire region, and node B is going to actually work in a manner that it's going to replace data in a more with finer granularity accesses into B. So it might be doing writes across the region of B while the as it's progressing through whatever computation it needs to do. I call this kind of the frame buffer type of thing. Going back to graphics, you had to incrementally work on different parts of the regions, but maybe you can't take blocks of those and put them into your own physical memory, or maybe that doesn't make sense, right? Because the region's so big. So in this case, you might be suffering the latencies of those remote accesses, but you do have all the cache infrastructure available on node B. But in this case, you'd map that as shared memory, so you can do what you need to do with it, and then you would be responsible for the flushing the caches on node B to get all that data pushed off and to get the consistency of the data back where it's needed before you transfer control back to A. And so, while both of these have different principles, these are both producer and consumer models, and it does require some coordination to basically share the data. So when that kind of gets us to the next model, because how do you efficiently do that the most effective in a most efficient manner? So that kind of gets into what network people have been doing a long time with point-to-point messaging. Right now, if we're not talking necessarily about huge buffers, but smaller ring buffers designed specifically for messaging communications, here's where it makes sense to have shared regions on both systems. So you have one-way communication going from node A to node B in a borrowed region, and then also have that symmetric view from B to A. And in this case, you can map these as IO type memory, and as far as the system's concerned, you can use the cut and paste mechanism to order those communication rights and to relax the ordering. And the premise here is that any region must always write to the borrowed region and pull on their local memory. And doing that gives you a very tight loop, where you may have one core devoted to pulling, but you're pulling on the physical memory, and you're writing with the ISA directed mechanisms out to communicate and push that data back to the node. And that's actually fairly convenient when you think about what's needed for messaging. I mean, the cut and paste primitives are two commands basically, where you're taking a message, and those two commands push the data all the way through. When you
Steven, sorry, you have 2 minutes left.
Okay. So when you think about how to do that in other systems with NICs involved, et cetera, that's a pretty lengthy process. So, as we go beyond point to point now, you have this, you have to establish now a network of these things. You might have seen from the Hot Chips presentation, where Power 10 processor sockets were connected to a large, Taurus-likes and Dragonfly-like type networks. I mean, if the Hot Chips presentation, I think it was done last year by Bill Starkey. If you want to look it up, there's a reference to the design guide. But basically, what that tells us is that the Power 10 has multiple MI Inception ports that can be routed at a system level between motherboard to motherboard to create these large topologies up to 1K nodes. And you're able to create these message passing regions with a shared global address space and a orchestration process to program the MI ports and the page tables on the different nodes to create very efficient message passing between, for instance, in this case, node A and node C. Node B is the outbound path, and the return path is actually a different path, just to illustrate that we require point-to-point connections, but because the address translation is done at each point, you don't necessarily need to go back the same point you came. So in this way, you can support large toruses and dragonflies, and this is the kind of stuff that you can scale up to 1K nodes. So I've said a lot in the 20 minutes, and I leave you with these references, though. Of course, you can get a hold of me for future questions. I mentioned much of these in the presentation, except for the VAST API. The VAST API is actually part of the kernel documentation in the PowerPC, and what that gives you is a notion of how you can connect a crypto accelerator in that API, and how you can move memory around with using the cut and paste primitive for the most efficient data type movement. So thank you, and Christian, I hope I kept us on time.
Yeah, no worries. Thanks, Steven. Now we can't wait to get one of those P10s and give it a go. Okay, so before we move to the next speaker, just a reminder: please post your questions to the chat so that we can start processing them, and we are ready for when the Q&A starts. We are ready to start posting the questions to the speakers. Okay, so the next speaker is Felix Heberhart. Felix, the stage is yours.
All right. Thank you, Christian. So in this presentation, I have two major topics I want to show you. First is, let's say, some early experiment results we did with an in-memory database on a Timothy's Flow prototype system. And the second is, or are basically from our perspective, some impacts we see on the operating system and on the applications when you are using disaggregated memory. These are performance, reliability, and architecture, but we come to that later. So, first, let's talk perhaps about the Timothy's Flow prototype we have in our lab. So we heard that with Power 10, there will be memory inception. But you can do memory disaggregation today. What you need is basically, from a hardware perspective, two IBM IC922 machines, or two Power 9 servers, two Alpha Data 9v3 Fpga cards with the Timothy's Flow AFU on it, and some network cabling, right? You can see that on the picture I have here. This is basically from our lab, our memory disaggregation prototype. So, of course, then you need some software, firmware patches you have to install on the machines, and Timothy's Flow is open source, you can get it on GitHub. And then you do basically configuration, and then you can claim memory from the remote server, and you see it on the on your host node as a computeless NUMA node, right? So, and once you have that, well, you can fire up some processes and enjoy load and store semantics. So we did that on an experiment, as I said, with in-memory database. We did that in collaboration with IBM Research Europe, the Next Generation Systems Group, with Christian, Mikel, and Panos, and from HBI. We also have, of course, some guys working on that topic, Andreas Carpentine, Lukas Wenzel, Sven Köhler, and Max Plaut. So what we did was basically using our in-memory database Hi-Res, which is also open source. You can get it from GitHub. It was developed on also on the HPI. And we think it could be a good fit for memory disaggregation. And that is for several reasons, right? If you think about in-memory databases and data processing, or in-memory data processing, you will have large memory footprints, right? Could be in the terabyte range. In-memory databases also have some bursty hybrid transactional workloads. So on the one hand, very small queries which update single data items which have to be processed very fast. On the other hand, huge analytical queries which require significant intermediate memory usage. And so we did an experiment to say, okay, let's take a standard database benchmark and see if we first execute it local, and then on the second experiment, execute it strictly remote on this borrowed TMSs flow memory. So we did that with an TPCH benchmark. It's a standardized database benchmark. As first, we executed it single-threaded with one client and one scaling factor to see what are some baselines, right, to work from there on. So first, let me say, of course, this is work in progress. So the results we have, and I will present to you so far, are reasonable, but well, they could be subject to change. So we basically pinned all the threads and the memory allocations to get these two scenarios. And now if we look at the graph below, where we have the query latency for the 22 different TPCH benchmark queries, we see that, well, some queries are heavily affected, others you don't see any difference at all, right? And overall, I would say it's rather surprising that the results are actually so good, right? So you nearly have all the queries in under a second. So this is quite good. But let's have a look at some of those very heavily impacted queries. So for example, here we look at query 9 and we do an operator breakdown. So every query, of course, in a database is decoupled into different operators, for example, a join, a projection, a table scan, and so on. Now, another spoiler. So these results here are currently not run on a TMSs flow prototype, but well, we are working on it. So these numbers are basically produced using a Power 8 scale-up enterprise machine, right? So one of those rather big E880 machines. And the reason is you have, let's say, similar behavior, right? So if you can also there construct two scenarios, one where you have local memory and one where you go beyond one of those enclosures, basically. So our machine has two enclosures, and when you go into these enclosures, you have 2 times the memory latency. So that is not as much as you get with TMSs flow, but it's well, near there, let's say it. So what we see here is, yes, we have quite some impact. So from 400 milliseconds to 550 milliseconds, but it's not, well, doubling, right? Which you could imagine when you have double the latency. We also see that some of the operators are more affected than others. And so this is basically the path we want to continue, right? Looking at, why is a certain operator more affected than another? Second thing is, you know, basically this is the worst case, right? Working completely or exclusively on remote data. What you can think of is, well, perhaps I want my raw table data on my local system and only the intermediate results needed for a hash stored on the borrowed memory. So it could be that that will improve the performance significantly. And it also is quite some, let's say, memory you could save in your in one of those systems. So for example, with a scale factor of 1, we have roughly about 1.5 gigabytes of table data. And for example, for query 16, and let me quickly go back. So query 16, first, you can see it's nearly not impacted, which is good. However, we see that at least for our runs, query 16 was the one with the most intermediate memory needs, the most intermediate allocations. And you can see that basically here on the flame graph. So the flame graph you have on the y-axis basically stack traces. So you can see where in your applications you have the allocations, and the width of the different, let's say, towers you can see here is the amount of memory allocated during the runtime. And for query 16, you can see that the most memory is allocated for a sorting step, for the aggregate hash, for a table scan, and well, for a hash join. And so perhaps it is interesting to say, modify the operators and say, you know, all your intermediate allocations, do not do that on the local system, but on the borrowed memory. Okay, so let's come to the second part. So with these experiments in mind, let's talk a bit about the possible impacts on the operating systems and applications. So first, let's start with performance. So we saw the experiments are kind of comparable to large NUMA systems. So those scale-up NUMA systems with 16 sockets or so. There are quite, or let's say there is plenty of related work, right? There are approaches and tools to tackle the NUMA impacts for applications. So all these could be used to work with those memory disaggregation or memory inception with Power 10. So you can say that latency more or less for at least some cases can be mitigated. Of course, bandwidth will be limited, and that will be a problem if you have a lot of cores working on parallel on this borrowed memory. However, you will also have synergy effects. Speaking of cache optimization, which you want to do anyway, right? For a processor, even the local memory is far away, so you want to have everything in the cache as good as possible. And so also these cache optimizations will also help for the remote or even for the borrowed memory. You have to be careful and decide on, well, case-to-case granularity, and you have to think about your data access patterns to your data structures. Because, for example, there are some data access patterns which are very latency sensitive. So, for example, pointer chasing. Think about the B+ tree or so, right, where you have a lot of data loads which cannot be prefetched, for example, right? So let's talk a little bit about reliability. Of course, not saying, you know, memory inception is unreliable, but, you know, the borrowed memory, or at least for Timothy's flow, the borrowed memory from the other system has its own system stack. So you have separate hardware, you have the firmware, you have a separate operating system running, and basically the memory comes from a process inside the foreign operating system. So what you can say is you have multiple or at least more points of failure, right? And this behavior, let's say, is new to shared memory apps. We know that, for example, in distributed systems where it's normal to have nodes that will fail and you can build software to tolerate that. Not so in the shared memories, in the shared memory world, right? So you could ask the question, so is it possible? How can we build fault-tolerant applications? For example, what if, you know, the memory is not reachable anymore? Do I get a ZIG bus from the operating system? Do I catch it as an application and then do what? A retry? Is it possible? And so on. Second part is how do we build a fault-tolerant operating system? So if you have, for example, critical kernel data structures on the borrowed memory and it is not reachable anymore, not good. So perhaps also for the operating system, we want to keep it locally. However, also here we have, for example, the hot plug memory functionality where you can basically say, okay, there's a memory region and please flag it as, I think, movable memory. So that I can offline it if I want to. And so operating system, please do not store any critical kernel structures on that memory region. And also all the work on distributed systems could be helpful here to think about, bringing some fault tolerance to shared memory applications. Lastly, architecture. So, most probably we will have heterogeneous memory regions. We have them kind of already today, right? We have, for example, volatile and non-volatile memory. We could have that in a system today. If you look at NUMA systems, you have local and remote memory. You could have, for example, buffered memory in your system offering high capacity, medium latency, medium bandwidth. Standard DRAMs with medium capacity, low latency, and let's say lower bandwidth than in the buffered memory world. Or perhaps you could even think of systems with DRAM and high bandwidth memory, right? With low capacity, high latency, and high bandwidth. And now with the borrowed memory or memory inception, thinking about the reliability aspect, you could say that we now have also different reliability. You have your local system and you have your borrowed or your remote system. So how do we deal with our applications? With that hardware, right? So what about software abstractions? Well, you can think that there are approaches, for example, using memory pools in applications. They are used, for example, in the real-time world, right? There they use them for allocation purposes to say, okay, I have one memory region where I have a worst-case execution time or a static allocation time. But you can also use it, for example, for these heterogeneous memory regions, right? So it would, and if your operating system also knows about your memory pools, it would have more flexibility of placement, right? So from an application point of view, you want probably differentiate on the one hand, intermediate and persistent allocations. We could here profit from work on non-volatile memory. And on the other hand, you can think about, let's say, new memory pools for example, different data access patterns. Now the question arises, how many different memory pools do I need? Which classes are worthwhile, differentiating for the memory pools? And how do I classify my data structures and parts of my application? Also here, we most probably want to do a data access pattern analysis, right? Which could help us to classify our data structures. All right, so let me quickly sum up. So we have some promising first experiments. We have quite a lot of research questions arising. We have plenty of related work to build on. We have a prototype available. Let's disaggregate.
Thanks very much, Felix. It's nice to leave the audience with a couple of open questions. Let's hope that we will stimulate their interest in the topic and have them do more research. So thanks very much. So let's conclude the presentations with our last speaker, Akos, and then we'll jump to the Q&A session. So Akos, the stage is yours.
All right, I'm sharing my screen. Do you have it?
I have a blank, but I can bring your presentation up.
It appears to be working on my side, so I'm not sure.
Oh, no, now we see it. Now we can see it. Okay.
All right, amazing. Yeah. Oh my God. All right, so yeah, as Christian said, I'm Akos from the Accelerated Big Data Systems group from TU Delft, and I'm going to be talking to you about opportunities and research ideas for disaggregated memory with a big data context. So let's go through the agenda. First, I'm going to mention some big data trends, some highlights, just to be on the same page. And then I'm going to talk a bit about how Apache Arrow, a new movement and data format, tries to shape the performance of big data applications, and also do some standardization. And then I'm going to elaborate a bit on how big data applications that leverage Apache Arrow could be deployed on disaggregated memory, and what would be the benefit. And after that, I'm going to mention a few new frameworks and a more mature one that uses Apache Arrow in the back end, just to see what's out there. After that, concluding the Apache Arrow stuff, I'm going to present a few more research ideas that aren't necessarily related to Apache Arrow, but still could be really good candidates for disaggregated memory. And I'm going to close the presentation with some Mimesis Flow contributions that we're doing to deploy it on our server. So big data trends, these are market predictions, but you're going to get the gist of it. So first, continue migration into the cloud, meaning that even companies that had on-premise data centers are moving into public clouds or hybrid clouds, partly because they need more processing power, and partly because some of these vendors offer so good services for storing and analyzing the data that it is really worth to use it. And also we see in-memory computation spreading. So developers realize that, all right, it is really worth keeping the data in memory and doing the number crunching instead of loading it every time from the storage. And surprising, but this is new in big data. And also edge computing. So whenever you can, just do the pre-processing and all the processing you can where the data is being generated before you push it into the cloud. And with all happening, in the meantime, the large increase in data volume and velocity obviously continues, but some of the resources that are necessary to process the data just remain flat. And with the companies becoming more and more data-driven, that actually means they're going to spend more money on compute resources. Every optimization we can do to these applications is going to result in savings. And even without considering the market trends and market researchers, we just pop up GitHub and we see a lot of new projects that are specifically focused on performance. And this hasn't happened before. So how a big data application looks like, what a big data application looks like. These applications are usually implemented as pipelines from multiple stages, and the variety between these stages is huge, meaning that inside the single big data application, these stages can be implemented in different languages, different frameworks, using different whatever, and somehow at the end they bundle it together and the whole pipeline does something useful. And if you look at this theoretical, but it could very well be a real pipeline, sometimes you write data back to the storage between the stages. Sometimes you keep it in memory, but not in the same format. So you have to do serialization and deserialization between the stages. Obviously, that takes up compute resources. So all in all, this looks very inefficient. And it's even worse when you start considering how would you deploy this in a cloud setting. You go and you would have to choose a node type with a particular amount of resources. But if you deploy this whole application on a single node, you see that we have stage 2 that uses high CPU and also a lot of memory. Stage 3 only uses a lot of memory. So even if you try to select the right node type, you're already doomed. So how can we solve this? Apache Arrow comes to the rescue. It's an in-memory data format. And the interesting thing about it is it's defined as a physical memory layout. So it has the same memory footprint across languages and frameworks. So you don't have the serialization and deserialization overhead. It's a columnar format. So your typical big data analytics algorithms are going to run very efficiently because you can utilize SIMD, for example. So from the ground up, it's built to be performance optimized. And since you don't have to do serialization, deserialization, sharing data between processes is actually just passing a pointer. It's zero copy. And I forgot to mention that it holds immutable data. This is very important. So what can we do on disaggregated memory with Arrow? All right, so seems like we would like to use a lot of memory, because in-memory computing, we have Apache Arrow to represent the data in a format that all the stages and all the frameworks can understand. So let's have a big pool of shared memory. And the key concept here is immutability, because even though this looks like a big shared memory pool, this is producer-consumer type, meaning that stage one produces the data, puts it somewhere, and then the rest of the stages can access it. So what do we need for that? An object store over a shared memory. But we already have that, because the Apache Arrow project, or this is unclear nowadays a bit with Plasma, but it has an object store already. It holds immutable data, meaning that the producer fills up the buffers, then seals the object, and then the clients can read that data. It already has good integration with a lot of frameworks and application. So how about Plasma on disaggregated memory, maybe? So these are the frameworks I wanted to mention, and you can see that there is a more mature one, Ray, and there are two very new developments. I just want to point out these because, as you can see, all uses Apache Arrow in their core to represent the data, just in different flavors. For example, Cylon uses Apache Arrow, but uses OpenMPI to distribute the data between nodes. On the roadmap, they have Mellanox's UCX that could use RDMA as well, I believe. Ballista, for example, that is really new. I think they're just voting on donating it to the Apache Arrow project. It has a Rust core, it's very performance-oriented, it's distributed, and it uses Apache Arrow, but instead of OpenMPI, they use Arrow Flight, which is the on-wire representation of Arrow formatted data. Currently, it's built to be transported over TCP, but they claim that they want to support RDMA as well at some point. So let's get to a real application that actually comes from our lab, ArrowSAM. SAM meaning that sequence aligned mapping. This is a genomics pipeline. So you can recognize a very similar pipeline here than what I showed you before. So the data comes in. Here are the multiple pipeline stages, and they all work out of the same shared object store that stores Apache Arrow data. Traditionally, this would look like, all right, we do the mapping, we write the data back to disk in whatever format, then do the sorting, then do mark duplicate. Instead of that, all the pipelines commit their data to the object store in Apache Arrow, ArrowSAM format that all the other stages can read and can read in parallel. So you spare all the I/O bottleneck that you would otherwise have with reading the disk or the storage. And moving on to not Arrow projects, we have a few more in mind. For example, grid simulations for brain simulation models. Here, the paper we cited uses RDMA between GPUs to communicate the neuron connections. We believe we could do something with this. Another interesting one is multi-agent simulations, for example, for biological cell development. The paper we cited here, the biodynamic paper, they claim that this is a very memory-intensive application. Just to put this into context, they claim that with 1 terabyte of memory, you can simulate around 3 billion agents. So if you were to have memory hot plug in this application, that's immediate gain. But obviously, these applications are not share nothing, and coherency here can be an issue. So this is something we're going to have to take a look at. So onto the infrastructure we use, we have an Inspur Power 9 system and a 987 accelerator card. As you can see, none of which was tested with the Mises flow before. So we're the first ones. And unfortunately, as you can see, there is a bottleneck here because the original Mises flow design uses 2 servers and 2 FPGA cards. And we only have a single one, and even that one is in a data center at TU Delft. So we don't have access to that all day, and we cannot crash it to our liking because it's half production, half development. So we came up with an idea. All right, so we wanna use Mises flow only for development purposes. So we added the 987 card support, and we are about to create a loopback design just for development purposes. The first idea we have is doing the loopback inside the FPGA. It sounds completely useless, but actually it's not, because this is a research question in itself. We reached out to multiple people and asked if it's possible to run a single OpenCAPI link in C1 and LPC mode at the same time. According to the specs, it should be possible, but to our knowledge, no one has tried this before. So we're going to be the first. If this works out, we're obviously going to implement this properly. So we're going to use the QSFP ports. And if all goes well, you're going to have you could use both the compute and memory side at the same time over a single OpenCAPI link. Obviously, if this doesn't work out, we just use the 2 OpenCAPI ports and put 2 AFUs on the FPGA. And with this cliffhanger, I would like to close my presentation. If you have any questions, feel free to reach out to me anytime, or ideas or remarks. Thank you very much.
Okay, thanks a lot, Akos. This was quite good. There will be questions. I have a few, so we will be looking at them now, actually. So now it's we switch to the question and answer. So keep your questions coming in the chat. Don't be shy. We have already a couple of questions in the background that we can start for warming up the audience. So let's bring them up.
So would you like me to start reading?
Oh yeah, sorry. Yes, I was trying to find it.
Yeah, no, it's okay.
Yeah, please.
We'll start with one that is for you, that I think is of interest to everybody. So I got a question through another channel about how and where this presentation, this webinar might be accessed afterwards.
So the webinar is recorded, so we'll for sure have it on YouTube and alike. The thing is, what we will do is that we will email all the participants registered with links to where to access the video and the slide decks. But definitely we will be sharing all the material.
Great, thank you. So since Alan was the first one who actually posted a question, Alan, do you want to actually ask your question directly to Steve? Ask Stephen. I mean, I can read it too, but since we can't hear you, Alan.
You're in mute.
Stupid mute button.
That's the nightmare of COVID.
Yeah, so enjoyed your presentation, Steve. So you showed a number of sharing options in the way this works, and I guess I'm a bit of a traditionalist. I like good old-fashioned shared memory, where you're in control of sharing. So when you actually had 2 ports on a real memory, and you would have letterbox and doorbells, And it sounded like in one of your latter descriptions that you were hinting at having that ability at a sort of small granular level. And then if you could do that, you could share a region of memory where the remote one could get into that memory and have sole access to it, and then negotiate access with the doorbells and letterboxes, and then hand it back to the local memory. So I guess basically that implementation, if so desired, would be very doable in this architecture. Or did I misunderstand?
No, you got it correct, Alan. I mean, that's definitely a possibility in the hardware. And the nice part about some of that, I mean, as I kind of alluded to in the presentation, the different ways that you set up the region are based off of how you mmap and how you malloc the data. So there are some application level controls over how that memory is treated. Ultimately, though, some of this is going to be, I mean, the security concerns around what the hypervisor lets you do and what how the processes on both sides access the memory, and whether will be interesting to see how that kind of goes out. One could definitely see, in the open community where you throw security access to the wind, that you allow any process to access the memory. But ultimately, as this, I think there will be a commercialized version that's more use case specific, that will control these mechanisms, and then there will be more of the open community, really the technology to its limit. So I don't know how that's going to progress as we bring the technology forward, but I do see.
I guess you could have the potential to enable a coarser granularity software-controlled memory sharing, as opposed to everything being low-level hardware cache managed, application managed potentially.
Yes. At the firmware level, the privileges of who gets.
Yeah, I get the point on security. Obviously, that's a biggie. Thanks.
Let me go to a question for Felix next. So, if we look at the typical base that an OS manages locality with things like C groups or NUMA control, do you think that those mechanisms are sufficient and we just have to learn to use them in a slightly different context, or do you think people need new mechanisms in the OS?
So the tools and the mechanisms you mentioned are quite powerful, and you can do a lot of with them, right? However, I think they are not enough because they work on a rather coarse granularity, right? If you think about it, they are more or less on the process granularity. So for a process, you can define on which cores it should run, or which NUMA nodes the memory comes from. Now, if we go inside an application, right? Now you want to have one data structure on one NUMA node, another data structure on another. You could do that with libnuma, right? Part of what you mentioned, NUMA control and all that stuff. True. But still, you have some limitations. Let me give you an example. Nested allocations, right? So you have, for example, a vector, which you allocate from one NUMA node, and then the vector in its implementation allocates further data items, data structures, but not necessarily on the NUMA node you were intended to. So I would say yes, there are certainly cases where you at least extend the mechanisms, or can, I don't know, think about other stuff. For example, these memory pools or so. Yeah.
Okay, thank you. So Christian, this was a question you posted. I can read it for Alan, or if you want to, you can ask yourself. You're on mute.
Yeah, I can actually ask it myself. So at the beginning of your presentation, Alan, you mentioned that memory pooling is challenging because of being latency critical, and this I understand, and also for reliability, accessibility, and serviceability. And then at the end, you conclude your presentation by showing an OMI-based prototype for a memory pooling server. So how is OMI overcoming these issues that you have mentioned at the beginning? I understand the latency, but what about the RAS, right? RIS?
Yes, it's a good question. Well, essentially, I guess at the beginning we're showing where memory is literally completely disconnected, but in the conclusion we're saying that memory should still be coupled tightly to the processor or a processor itself, and it's then can it also very effectively share it with others through a fabric. Obviously, yeah, the latency is one that you will take with sharing, but I guess it's acknowledging that that a pure memory pool itself is, you know, is that purely valuable, and can you bring the two together? You know, you have your own local memory for the ultimate in latency and RAS, and then you can share, and you do have to take the necessary latency. The RAS is you can maintain reliability, but I guess again you need better mechanisms for retries across fabrics, etc. So you need to handle those more effectively, which again I think with the Memory Inception implementation, you've got some significant efficiency implementations. It's not designed to work across a switch, for example. So you've got to make your compromises depend on how vast and flexible you want your composing network to be, if that makes sense.
Yeah, I mean, I think that the reliability bit is one of those that we should be starting looking at, right? If we want to scale up these systems,
right?
Because point to point is, of course, it's limited, but it's limited because we want to have limited issues, right? That we take care of. So definitely, it's an open research question actually, and let's see what will come up in the future. Yeah, thanks, Alan, for the.
So then I actually have a follow-up question for Stephen. So you may want to so basically, can you say a little bit more about latency and you know, I don't know if you can talk about it in absolute terms, but you know, maybe comparing time history flow to, you know, bolting the text together as Felix showed versus this, and maybe also a little bit about you know, point to point versus fan out.
All right. Yeah, let me try to take this. I didn't even think about comparing it to Thamesis flow, but I think when we originally did that estimate, it was about 10 times faster than what you would get on Thamesis flow. But you know, that being said, I think the easier way to say it is that, you know, this is it's going to be network attacks. DRAM is already demonstrated faster than storage class type of local accesses, right? So you get into more of the RDMA accesses. This path is definitely more efficient than that path because you're eliminating NICs and any kind of software interrupts. So really, the best comparison is to say if you know the latencies that you see on SMP systems are the best representation of what you'd expect for memory latency and for memory inception.
Great, thank you. Christian, I see that you also had a question for Akos. Maybe.
Yeah, exactly. I will ask it. I will ask it myself. So Akos, it looks like that the object store that you have mentioned for Apache Arrow looks like let's say that its natural extension is to be ported to disaggregated memory, right? So probably the Plasma. I couldn't remember the name. So probably because this way you could have a huge share space in memory. But then this makes me think that disaggregated memory or memory inception will allow you to do this sharing across machines. So is Plasma already working across machines, and then you can leverage this new mechanism for simplifying the way the way it scales across machines, or this is not seen and this is not this is not supported, and then going across machines is right now somehow solved by Apache Arrow. So introducing disaggregated memory into Plasma will also simplify the way how you scale up a Plasma workflow across machines.
So you're exactly right. Plasma doesn't support multi-node just yet, but this is something that the community is looking at and really wants to have. I just looked at the mailing list, and there were some requests about this. So currently, the only way to do between nodes is using Arrowflight or OpenMPI, or using one of the frameworks that can actually deliver your data between nodes. If we were to extend Plasma to multi-node, and actually that's the plan, because this is really convenient, because we only need to do some housekeeping, not very much. So this would be a really convenient way to scale Apache Arrow-based big data pipelines across nodes.
Yeah, because basically you can remove any also you can remove dependencies from frameworks that let's say enable this scaling in software, right? You would just
exactly. So this replaces a lot of magic in already existing frameworks. This will be really clean and simple solution to deliver data between nodes.
Yeah, especially because of the immutability, right? Because I mean, since what we have seen with in the presentation, Steven's presentation, that somehow coherency is not bilateral, right? And it's not easy. With the immutable objects, this is like looks like the perfect.
Yeah, it's like this one was built for disaggregated memory. Yes.
Okay, so looking forward to see the next step for this. And I had another question. I'll go ahead with this. This one was for Felix. Yeah. And so Felix, you mentioned that, let's say, the disaggregated remote memory is inevitably going to have a higher latency, and we could probably, one way of mitigating this is going to be relying on what the CPU cache is doing already for DRAM. But I'm wondering, I mean, is this going to be enough? I mean, if we are talking about sharing huge amounts of data and applications not necessarily having a cache-friendly behavior, is the CPU cache going to be the solution, or do you believe we should slot another memory layer in between, such as using the local DRAM or HBM for staging data before hitting the cache?
Mm-hmm. So on first thought, I would say, I mean, we have several cache levels today, so why not add, a fifth or a sixth cache level? The question would be where to place them. So, for example, if you think about placing a cache on the remote system, which is extremely fast, but you cannot, let's say, transport the bandwidth between those systems, that's probably not such a good idea. On the other hand, if you have data access patterns which are not cache friendly, more cache wouldn't probably not solve your problem, right? For example, in this pointer chasing style of access, right? You could have, I don't know, 10 cache levels and you would miss on all of them, right? So, and on the other hand, you also mentioned, so what to do about, let's say, really large memory footprints and processing them. So if you have like cache-friendly data access patterns, you could, to some extent, I mean, if the latency doesn't go crazy, rely on the prefetcher, right? And then hide the latency with that mechanism, right?
Okay, sounds yeah, makes sense. It sounds interesting. Okay, thanks, Felix.
Okay, I had one more for Alan. I mean, we've seen from your presentation and the others, right, how OpenCAPI and OMI, you know, works beautifully together, and you can create certainly very interesting systems with power technology. You know, can you get any benefit of this if you you know, if you have a more you know, if you have commodity infrastructure or non-power architecture systems?
Right. So I think, well, there's two pieces to that in my mind. We do have the OMI piece that I talked about, and then we've obviously got the sharing piece with either Phimosis Flow or Memory Inception, which is obviously Memory Inception is power based. So firstly, from a OMI differential DIM perspective, hopefully the attraction of that is clear. Obviously, it's natively implemented in Power 10 today, so yes, it's specific to the Power 10 architecture. But it's fully open and it's available from the memory vendors, and so anybody can implement it on their processors. It's been fully implemented on Xilinx FPGAs today. And so to give you an example of the potential just with an FPGA, you can have 4 DDR4 memory channels on the biggest FPGAs today, or you can have HBM, 2 channels of HBM with 450 gigabytes per second or thereabouts. With OMI on the larger FPGAs, you can actually approach 700 or 800 gigabytes per second, so you can exceed the bandwidth of HBM with the transceiver attached to OMI differential DIMMs on Xilinx FPGAs today. So people that have data-centric type problems and have their own algorithms running on FPGAs, in their memory bound, they could certainly immediately benefit from OMI differential DIMMs. As well as that we are seeing many silicon startups with different accelerator general purpose processors and accelerators. So silicon is popular again with venture capitalists. If you have a special secret sauce in your algorithm, you want to be focusing on that, and you don't want to be second guessing whether to put DDR4 or DDR5 memory on your processor. So if you put OMI, you're going to get silicon back for your valuable core focus, and you're going to be agnostic, so you can ride the wave of whenever DDR4 gets replaced by DDR5, as well as potentially plugging in other memory technologies in as well when they become available. So I think there's an opportunity there for VC-backed processor startups. There's some interesting stuff going on in the background that we can't talk about, but it looks like the OMI differential DIMM is the way to go there. Now on the borrowing side, I think you know, so on the Phimosis Flow and Memory Inception side, clearly Phimosis Flow has been demonstrated today is being fabric agnostic. Obviously it's connected to the OpenCAPI port today, but we can see as CXL gets more and more mature, it can adopt some of the findings from this research for potentially borrowing from this. So this research is for everybody, and I think there's some valuable findings here of as we find a way to disaggregate memory. I think what we're saying, my conclusion was, you know, we do need to have very efficient coupling of memory, scalable, flexible, composable, as I said, and with processors, and OMI gives that, and that's fully open today. And then we can still have innovation, or we can use Ethernet. We can go across the internet with Phimosis Flow, for instance. You're dealing with big latencies, but it's still possible. and communicating with an edge of network, a data center with an edge of network, this might be a very interesting setup for people. So I think this is for all. This isn't just focused on power at all.
So we just had another question posted to the chat from Panagiotis Kutso Vasilis. So for Steve Roberts, what are the reliability standards for Memory Inception on P10? How to recover from network failures?
So that work is early. We've done some of these before. I mean, we have the same issues with OpenCAPI connected devices, right? I mean, if you think about this, this is a point-to-point communication problem, and we of course address this in the hardware and in the software stack, but we're able to reliably communicate between an accelerator and the processor. And so what you've done now is, yes, you've added a link across that might span across a rack in the data center, and that will present some interesting challenges. But we have a pretty rich history in SMP technologies where these cables do go node to node. So while the software recovery is going to be different than the SMP case, the same standards of the hardware can be maintained, and you have to also map that against like I said, with just a load and a store, you can actually push a transaction across the bus. So if you think about the software layers you've just taken out of the system, there's a concept of, okay, did I gain reliability by reducing the software stack? And so it's a fairly good mix, but I don't have a canned answer to give you now, just to let you guys know that we're working on it as we commercialize the technology.
Yeah, and I know Felix, actually, you commented on this a little bit from the OS software side, right? I don't know if you want to add something.
Well, for us, these were initial thoughts, so I also cannot comment if it's ultra reliable or not reliable, but I think there will be some challenges. That's what I think is.
It's certainly a solved problem in the terms of network message passing. You can apply the same things that you do on unreliable networks. It's really the direct load store semantic type models that become the more novel of the use case. So yeah, there are some ideas, but I think that's for a different webinar.
Right.
Yeah, but perhaps the difference with message passing is that with message passing, your application, let's say, knows that it might fail, right?
Right.
The exchange might fail. The CPU might be a bit more, let's say, picky about data not coming back. So yeah, I think that probably will be a mix of operating system and hardware.
And just to comment on that, so right, if you look at distributed systems and message passing, we today have system architectures where you have checkpointing and restarting and all that stuff, right? But at least what I think is with Memory Inception, you basically have huge shared memory applications, and so this could be a different aspect.
Stephen, if you don't mind, can I give a viewpoint on that question?
Sure, Paul.
So I would expect, as it is a memory construct, that your reliability would be equivalent to the reliability of your local memory, which is subject to the failure of DRAM, right? So that's still going to be there. The network reliability has CRC and error checking and retry built into the hardware protocols. So the network is protected by the OpenCAPI link, which has reliability across that and protections. And the memory itself you're sharing, since it's not persistent, if you have a DIMM failure, right, you have the same escape to reliability as you do in a local memory. So I think it'll be equivalent to local memory reliability in that direct point-to-point statement.
Right, and on that, there was a question from Andreas Krappentown to everybody. The load store semantics to a failing memory device would just introduce a SIG bus, no? So I don't know, Stephen or Paul.
Correct. It'd be the same as, like I said, I think from a software perspective, any failure would look like a local memory failure. And the reliability of that should be very equivalent or close to the mean time between failure of local memory, because you are still backing it by DRAM, most likely in this case.
Good. I think we've answered all the questions that I'm aware of, so I'll hand it back to you, Christian.
Yeah, I think we let's say all the questions that we had and the few that came in. So I think we can close this day today. So thanks very much everybody for joining. We hope you enjoyed it, and let's say goodbye till next time. Perhaps there will be other iterations of this workshop if interest was high enough. Thanks very much to our speakers for sharing their insights on this field, and then for leaving us with some open research ideas that will let's say it's good food for thoughts. We go back home and we keep thinking at new things. And as I said before, there will be we will probably email all the registered users with the details on where to download the decks and access the registration of the webinar. So thanks very much everybody again, and have a good day or good night depending on wherever you are in the world. Thanks.